Hi everyone. In today's lecture, we will talk about several machine learning algorithms. And before that, I want you to notice that certain algorithms we will discuss here, including the KNN, SVM, CART, they work for both classification and regression problems. Okay, now let's get started. The first thing I want to talk about is that they need to apply multiple algorithms to solve a certain problem. This is because we never know which algorithm actually performs the best for a specific problem. So we often evaluate a diverse set of algorithms on our dataset and then choose the one that gives you the best predictive performance. Now, I will introduce the machine learning algorithms one by one. The first is the simplest and the most commonly used one, the logistic regression, which is a specific case of, which is a special case of GLM. And logistic regression is for binary classification problems only. Logistic regression is actually borrowed from the field of statistics, and it's the go-to method for binary classification problem because it's not only very easy to use and understand, but also often it performs very good for most of the problems. And basically, logistic regression tries to find the relationship between independent variables and the probability of particular outcome. So the probability of the output can be represented using this conditional probability. So given x, what's the probability of y equals 1? And then we can predict the probability using the logit function or the log odds function. The next algorithm is called naive Bayes. This is also used for classification problems only. It's one of the most popular machine learning classification algorithms, and it's based on the Bayes theorem. I bet most of you must be familiar with this equation. So this is the posterior probability, and this is the prior, and this is the likelihood. This is the predictor prior probability. So if you remember, the Bayes theorem actually assumed the independence among independent variables. And so the naive Bayes also rely on such an assumption that for each of the independent variable, it's totally it's independent from all other features. However, when we apply naive Bayes classification algorithm in real life, we can often find that the assumption can be violated. But actually, this doesn't make a very huge difference because naive Bayes actually often you can find it has quite good performance even the assumption is broken down. And that is why it's a popular machine learning classification algorithm. The next one is a k-nearest neighbors called KNN. KNN can be used for both classification and regression problems. It assumes that the similar things exist in close proximity. In other words, the similar things are near each other. This is quite similar to this saying, the birds of a feather flock together. So let me give you an example. So say if we have a new instance X, we want to decide which of the three classes X should belong to. Then we can first decide the number of the nearest neighbors. So the K, maybe we can let K be 3 or let K be 4. Then we calculate the distance of X to its 4 nearest neighbors. and then take the mean of the distance. So if the mean distance is the smallest for this class, then X should belong to this class. So KNN make predictions using the training dataset directly. And the predictions are made by searching through the entire training set for the k most similar observation, or the k nearest neighbors, and then summarizing the output variable for those k observations. So how do we summarize the output variables for the k nearest neighbors? So if it's a regression problem, we just take the mean. If it's a classification problem, we just take the mode, or the most common class value. And the k here is actually a hyperparameter that we need to tune. So the value for k can be found by algorithm tuning, which is also called validation. We will talk about this in our next lecture. And it's a good idea to try many different values for k. For example, we can try 1, 2, and until 20 or 30, one by one, and see which value of k works the best to solve the problem. So that's about the KNN. Next, we will talk about the support vector machine, or SVM. SVM is also used for both classification and regression problems. The objective of SVM is to find a hyperplane in an n-dimensional space. Here, the n is the number of features, and such a hyperplane can distinctly classify the data points. So, for example, if we have two features, that means we can represent the feature, each of the feature as an axis, so that we can have this two-dimensional space. And in this space, we want to find a hyperplane. In this case, it's a line to separate the two classes. And if we have three features, then the space should be a 3D space, and the hyperplane should be a plane. So we want to find a plane to separate the classes. And you may notice that there can be many possible hyperplanes that can be chosen to separate the classes. So for example, in these 2D dimensions, we can have so many lines to separate the two classes. So which one should we choose? The support vector machine states that we need to find the plane that has the maximum margin. So what is a margin? A margin is the distance between data points of both classes to the hyperplane. So for example, you draw a line between the classes, and then you draw two parallel lines. Each line goes through the nearest data point to the hyperplane, and then you calculate the distance. And the hyperplane with the largest margin is the optimal hyperplane. And those two nearest two most close points in each class are called support vectors. So that is why this algorithm is called support vector machine, because the support vectors are very important because they decide the optimal hyperplane. And the optimal hyperplane is actually the decision boundary, which is used to make the classification. So here you can draw a line and calculate the distance. Then you rotate the line until you find the margin which is maximum. Then we can say this is the optimal hyperplane. Another thing that is important to notice about SVM is that it uses a kernel. The kernel in machine learning refers to the kernel trick, which is a method of using a linear classifier to solve a nonlinear problem. Because in real life, we often find the problem is not a very simple one. We cannot just separate two classes using a single line, but maybe the line can be very complex. So in this case, we can use a kernel trick, which is involves some mathematical calculations. So we won't go into detail, but you should know that we can use this kernel trick to convert such a nonlinear problem to a linear problem, so that we can model the linear. We can try to model the linear line to separate the classes, and that will make the problem much simpler. So that's about SVM. And next one is the CART, the Classification and Regression Trees, which is one kind of decision tree. And the CART can also be used for both classification and regression problems. So the CART is actually a kind of decision tree algorithm that can be used for classification or regression problems. And some other algorithms that decision trees can use also include ID3, C4.5, and so on. And different algorithms actually use different metrics for measuring the performance. For example, the CART uses the Gini impurity, and the ID3 and C4.5 uses the information gain. I won't go into detail here. And the basic idea of the CART is actually we can represent the model using a binary tree, meaning that at one node, we can present a condition. If the condition is met, we go to one branch. If it's not met, we go to another branch. So that is called a binary tree. And also, such a binary tree can be represented using a set of rules. Like here, we can say the rule 1 is that if the height is greater than 180 centimeters, then it's male. The second rule is that if the height is not greater than 180, then and also if the weight is greater than 80 kilograms, then it's male. The third rule is that if the height is not greater than 180 cm, and also the weight is not greater than 80 kilogram, then it's female. So these two are equivalent. And you can see such a CART model because it can be represented by a binary tree or by a set of rules. So it's very easy for us to understand and also to interpret the model to others. Finally, there are some algorithms for regression problems only. The first one is linear regression, which you are very familiar with. So we try to find a linear relationship between the input X and the output Y by minimizing the error. And the second one is the regularized regression. So when the OLS assumptions are made, the coefficients produced by OLS are unbiased, and of all unbiased linear techniques have the lowest variance. However, in real life, the problems often have many features. And as the number of features grow, our OLS assumptions are typically broken down, and our models are often overfit the training sample, causing the out-of-sample error to increase. This is called the overfitting problem. In other words, an overfitting problem means that we have too many features so that we need to fit a very complex model to perform well on the training sample. However, due to the complexity of the model, it doesn't perform well on the new datasets. So that is called overfitting because it fits the complex training sample too well to make good predictions for new datasets, or it fits the training set too well that it has bad generalization ability to new data points. And one method to solve the overfitting problem is the regularization methods. So it controls the regression coefficients, reduce the variance, and decrease the sample error. And also, because of the overfitting problem, we should notice that it's not that the more complex the models are, the better they perform. But often we actually don't encourage you to build very complex models to avoid the overfitting. And another thing, another concept in contrast to the overfitting is called underfitting. So the underfitting means that the model doesn't fit the training sample very good, and due to that, due to the underfitting, the model cannot make very good predictions on the new datasets. So actually, there is often a trade-off between the overfitting and underfitting. So if the model is too complex, we have the overfitting problem. And if the model is too simple, we have the underfitting problem. And both underfitting and overfitting are not good for the prediction. So we need to use the validation to decide the best parameters. And yeah, in that way, we tune the model to avoid underfitting or overfitting.